Welcome back to Biotechnology and Biodegradable Materials. Today, as it says on the board, I will be wanting to concentrate on slower types of biodegradation, which, as we had in our first thing, are not normally considered to be biodegradation, but if we were looking at nature or things that last a long time, we would be interested in what happens to things over a long period of maybe years, maybe even decades, chemicals that escape into the environment. So let's have a look at some of those. The benzene ring would be a good example because that doesn't break down normally very quickly at all. In fact, if we look up the Wikipedia, for example, on biodegradable polymers, it will tell us that most esters are biodegradable, but not those with benzene rings in, except the one that we use, which is PET. It has a reasonable biodegradation, but it's not very fast. If we look at one of these molecules, we can see the problem. It's quite difficult to add things to it. We can see it from an organic chemistry point of view. The ring is relatively stable. It's comparatively difficult to attack. But there are enzymes that can attack it, and those enzymes would be those that deal with lignin in wood, because lignin in wood is a cross-linked version of this. So here I am back with better lighting. Try and make my microphone not do anything irritating. Here's my benzene ring, and what I'm going to do to it, what did I have last time? Toluene, I think. And the question is, what can we do with it? So as we know from organic chemistry, and benzene ring is not very good at reaction, but it does do or participate in electrophilic reactions, so we can remove electrons from the ring, and that means that we can oxidize it. Loss of electrons is oxidation, so we can imagine an oxidation reaction with our toluene in this case. So it would then oxidize, and if we do that with oxygen, we will end up, ooh, that's not very good. Hoping this isn't a permanent marker. Oh, good. We will end up, if we resolve that, we'll end up eventually through a relatively long pathway with an OH on here and the double bond back again. There is an enzyme that does this, and it's known as Lactase. It is also there are also other enzymes that are responsible for food going brown, which are phenol oxidases, and they help these ring groups to connect to other ring groups and make bigger molecules. If we add enough OHs to our molecule, we will make it organically acceptable. So now it's become more soluble. It's still fairly toxic. If we add some more, it becomes a normal organic molecule that's part of biology. How do we make this more difficult, however, is the question, because that might be the problem, that somebody has deliberately made it more difficult, and that will be the chemicals that are going to challenge our biodegradation. So just as before, if we have a methyl group on here, what it's really doing is pushing electron density into the ring, and that's good because that means that the electrons in the ring are more reactive. A toluene group is more reactive than benzene on its own. But if instead of pushing electrons into the ring, I pull them out, let's have trinitrotoluene. So if we take trinitrotoluene, which has the nitros on this group, so this would be the nitro groups, and they are pulling electron density out of the ring into this nitrogen, into the oxygens, or through the nitrogen into the oxygens, and that obviously makes it much more difficult for this ring to react. So trinitrotoluene, or TNT, is much more resistant to this type of oxidative reaction than normal toluene, or normal TNT, normal toluene. If we instead put chlorines on there, we will get the same, but it's easier to draw. If we put chlorines on there, we get trichlorotoluene, but normally it would be phenol. So we would have trichlorophenol, which is a normal, fairly common disinfectant. It's not supposed to be a double bond, sorry. That is obviously also going to be much more difficult for anything to come along and oxidize it, to remove electrons from it, because the chlorines are pulling electron density out of the ring. So what's biology going to do? Biology can still attack it. So there is still this chemical, lactase, which is an enzyme that is really there to deal with these phenol groups, and one of its side reactions is to remove these chlorines. What it actually does is it grafts an oxygen on here, so it grafts an OH on. That will cause, hang on, let me stop. Okay, so I had a meeting in between and I got confused as well. So let's have another look at this. Let me see if I can zoom out a little bit. No, I can't. Bring it down a little bit so that you can see it better. So we have our trichlorophenol. It needs to be oxidized. That's what happens with the lactase. It's a copper-containing enzyme that can steal an electron. It gives it finally to oxygen to make water, but it can't do that, obviously, or oxygen can't react directly, so the lactase is the intermediate. We are oxidizing this bond up to the double bond, so we're oxidizing the alcohol up to this carbonyl group. That obviously, or sort of obviously, means that one of these bonds has to move around so that the oxygen can have a double bond. Or we could have a radical here, but it can reorganize itself. Then we can attack from here with an OH, from water, for example. We can't attack from any other point because we need to push the electrons into the oxygen. Once we get the oxygen, I'm going out of shot, but anyway, once we get the electrons into the oxygen, we can generate this species, which you can see our aromaticity is even worse than in this case. We've shifted them around a little bit, and then we can reform our aromatic ring because we get quite a lot of energy back out making this cyclic electron structure. So if we lose HCl, so if we can eliminate hydrogen chloride, we can form back to our ring, our six-membered ring, which would be like this, and we have managed OH, Cl, we've managed to get rid of this chlorine on the bottom and form an OH here instead. So we're gradually getting towards what we would like to have. You can see that there is a lot of difficulty here because the thing that is attacking is a negative species and the thing that is leaving is actually a proton, this H+, and so it's only because of the last step where it recyclizes, right, where it reforms the aromatic structure. Where the ring reforms is the only step where we can get rid of the chloride ion, because we need to get rid of Cl-, and really what's leaving is H+. So that is fine in this case, but if we want to make it more general, this reaction is, or this type of reaction is relatively slow and relatively difficult. This is unusual that it works. It's used industrially to do this kind of thing, but it's not the only way that we can do it, because we can see that exactly that removal of electrons from our ring is made difficult by the presence of the chloride. So instead of oxidizing it, we could reduce it. Okay, so there is another way to get halogens off molecules, let's have a quick look at that. So it's the reaction that we would know. Can you see that? Yeah, you can see that. It's the reaction that we would know from before, which would be an SN2 displacement. So let's have OH minus, and that will go to finally, that will be SN2, and it would go finally to this alcohol instead. And there isn't an enzyme that does this. It does an SN2 reaction, so it doesn't matter that it's a chloride functionality in the substrate that we want to get rid of. It could be anything. But the problem with that is because it's SN2, it won't work on an aromatic substitute. So aromatics are more resistant. That's one of the problem chemicals that we're going to have to, or that we're going to accidentally end up with, or deliberately. If we find that our halocarbons keep disappearing, the aromatic ones last longer. But reductively, we can get rid of it in a different way. So reductively, we will be able to remove the halogen and go back to the alkane formula. So the alternative is, instead of to oxidize it, would be to reduce it. And if we're going to reduce our ring, we have to give it electrons, obviously. Let me have my triphenyl and trichlorophenols. I need to remove electrons from it, give it electrons, sorry. I can't give electrons to the ring because it's already got a lot. So one place to give it is this chloride, which is drawing electrons to it. So I could give it an electron here. And if I do that, it will tend to break at this bond. So that would tend to break in this way, forming a radical. And that enables me to remove one chloride. Why would bacteria be doing that? They obviously are not doing it deliberately to break down trichlorophenol in the water. They have a side use, or they have an accidental use for them. And that's because in anaerobic conditions, they are stuck with somewhere to dump their electrons. Sorry, let's have it. They're stuck for somewhere to dump their electrons. Normally, in the air, we would respire by giving our electrons to oxygen and taking them from glucose. But if we have a source of glucose but no air, which we might have at the bottom of the lake, we can give our electrons to other things, such as our trichlorophenol, and get rid of them onto it, which is good because it starts the process of removing the chlorines. As soon as enough of them are gone, it is then susceptible to oxidative decay. We have established that it is generally susceptible to oxidative decay, but there are some compounds that are much more difficult to remove. So, for example, if we put a fluorine on there instead, it would be much more difficult to do the oxidative pathway. This one works in other cases where the oxidation doesn't. So here we're doing a direct reduction. The reduction, an extra electron ends up on here, and we end up with a radical which can then rearrange. That is fairly normal for respiration processes. If we have a ring, the radical can be distributed, so it is a relatively low energy radical, so that is the kind of thing that the bacteria will be trying to dump their electrons onto, or better said, they don't care. They just push the electrons out and they go on to whatever chemical is the easiest to reduce, and that typically is one of these interesting molecules, which is difficult to get rid of in normal conditions because it's hard to oxidize, but it's completely reducible. Once we've got rid of the chlorine, as I said before, once we've got rid of the chlorine off the ring, it then becomes way more reactive and can be broken down in the normal way, can be oxidatively cleaved. The normal way is to open the ring using an oxidation reaction, but it can also, once it's turned into the dechlorinated version, it can also be used in normal reactions, because there are perfectly normal reactions of organic species with aromatic groups in. My sound got lost, so I have to switch to a voiceover here. What I was actually talking about here is alternative versions of accidental biodegradation or degradation by bacteria that may not be deliberate. So in the case of the chlorinated parts, it's usually either an enzyme that was used for lignin or for something else. Now I'm moving to iron. So if we take, for example, a piece of iron, does it biodegrade? Well, not really, but it can degrade due to the influence of bacteria. The first thing is the same as with teeth, that the bacteria will do some kind of activity, use up the oxygen locally and generate a corrosive environment, possibly an acidic environment, just like they do on our teeth. That's not deliberate, that's just because of the anaerobic degradation of organic matter creates an acid. But another alternative could be that they actually want iron, because iron is a limiting factor in many biological systems. So they are trying to extract iron from the environment and they just happen to be next to a piece of metal. That makes them very likely to be able to get some iron. So what they're doing is letting out chelating agents into the environment, so chemicals that will wrap around the iron and make it more soluble, and that will make the iron oxide more soluble. They don't really care about the iron in the middle, they don't even know it's there. But when the iron oxide dissolves, then the iron will become more bioavailable. It will become oxidized, generate iron oxide, and then that will also be removed in the same thing. Now I'm going to draw an iron and some chelating agents, which would have at least two sites, maybe more. If it's a protein, it might wrap around the whole iron and take up all of its potential sites, which is 8 in the case of a transition metal. In most cases 8 or 6 usually, but in this case for iron it's usually 8. I'm talking quite a long time about this, so we can see how that goes. Here I am trying to draw it. I'm not entirely sure what I said at the time. As I say, the sound got lost. So here I am drawing a chelation agent. Badly, that would be one that just has 2, and then in the extreme case those would be connected together by an outside molecule. The thing about chelation is it is particularly effective because we have, instead of tying up 8 separate molecules, we tie up 3 or 1, and if we do that then we don't lose as much entropy, and so the whole process is much more likely, much more driven by free energy considerations, and so we will tend to create the complex much more easily, and those are soluble, so it will tend to be removed, and then the bacteria will absorb it, but doesn't stop other things from taking it in or from floating away. It's all outside the cells. My other point was that we have 2 possibilities. We have oxidative processes, which happen in the environment with oxygen, which we might be involved in to burn sugars, but they will accidentally or deliberately also do other things. And we have anaerobic processes, which might happen at the bottom of a lake, the bottom of the sea, or in the ground, where oxygen is used up by bacteria, so the environment goes anaerobic, and then we have a reducing condition. The bacteria aren't really trying to reduce any chemicals. They're not trying to degrade fluorobenzene or something. What they're actually trying to do is get rid of the electrons they have left over once they've oxidized something, which they then have to dump on something. What we know from us is that anaerobic metabolism is extremely inefficient, and it's much better if we can give the electrons that come from the glucose typically to something else, another molecule. And what bacteria tend to do is they find something in the environment, so it will be sulfate in water or nitrates in water that tend to get reduced all the way to nitrogen or to sulfur, sulfides, and that will tend to it generates new compounds. And so in the case of sulfides, it's more toxic compounds, which is good for the bacteria in a way. In the case of yeast, it uses up the oxygen and makes the environment less conducive to other things that compete with them. But it can also denitrify, for example. It can remove the nitrates from the bottom of the lake. What happens then is, if we have a molecule, an artificial molecule that can be reduced, such as our chlorobenzenes, they can be reduced by giving them electrons, and they just function for the bacterium as that side of the redox reaction. But for us, that's really handy, because we've chosen those molecules because they're stable, because they're resistant to oxidative decay, but that makes them particularly resistant to normal biodegradation. However, going back to the theme, although our official definition of biodegradation is requires a certain amount of time, and to degrade to a reasonable degree, that's the official definition. So a sample of a specific size in a normal compost will degrade after about 21 days, so that you can't find any bits after sieving it. That means that the pieces left over are smaller than a certain sieve. It doesn't mean that there's nothing left. That is not relevant to this part of the topic, because we're thinking about much more persistent pollutants, which are broken down in a completely different way. They have to find their way to an anaerobic site, or they have to be attacked by these relatively rare lignin decomposing enzymes, which will come from bacteria that are specialized in using that as a source of energy, or and bacteria that are specialized in using things like coal, and so very low and difficult types of energy sources for bacteria. I don't know what I'm talking about now, so I'm just going to cut myself off, because I can't remember what I said. But this will be the last thing, because we've run out of time. I don't want to keep adding things after this week, or during this week even. So we'll leave it here.